Okay, everyone, welcome back. Today we're going to continue with Chapter 3 on polynomials. We're going to take a look at 3.1, graphs of polynomials. So a polynomial function is simply a function that has a whole bunch of powers of x, each one potentially multiplied by a real number, and then added or subtracted together. The domain is going to end up being all real numbers because there's nothing here that we're doing that would be one of our domain issues. So there's no square rooting, no division, and no logs. Therefore, the domain would be any possible number for x. There's a bunch of different pieces of a polynomial that we'll need to be familiar with so that we can talk about them moving forward. The degree of the polynomial is the highest power that shows up. Typically, when writing it out in this form, that's going to end up being n. The leading term is the term that goes with the highest power, an x to the n in this case. The leading coefficient is an. That's the coefficient within the leading term. And the constant term is going to be a0. Notice that this has to do with the highest power, not the order. So when the polynomial is given to you, if it's not written in the proper order from highest to lowest power, then make sure you look for the highest power when you're looking for the leading term and leading coefficient. The constant will always be the part that doesn't include a variable. If I simply have only a constant, then the degree of the polynomial will be 0. Unless the polynomial itself is equal to 0, in which case we will simply say the polynomial has no degree, as there is no highest power because there's no power at all. Now, one thing that we would like to be able to do is we would like to be able to understand how a polynomial looks just from its equation. So let's just go ahead and take a look at a couple of very basic polynomials. In this case, we're just taking polynomials that have a single term and a coefficient of 1. And we're going to make rough sketches of each of these. Now, some of these we've seen before. Some of these we haven't. So let's just make a bunch of coordinate plots for us to take a look at. So if I was going to graph y equals 1, that's just a constant line. Slope of 0, intercept of 1. For y equals x, we know that's for mx plus b, a slope of 1, and an intercept at the origin. X squared gives us a parabola, like so. Starting to look at x cubed, these are starting to be things we haven't seen before, but we're going to notice a couple of patterns. First of all, as x grows, the function is going to increase even more rapidly, except for near the origin. For small numbers, numbers between 0 and 1, the higher the power is, the smaller it will be. For example, if I had 1/2, the more times you multiply by 1/2, the closer you get to 0. The other difference between this and a parabola is the negative numbers. If I take a negative number and square it, it will turn positive, hence why the parabola looks like a bowl. But when I cube a negative number, it remains negative, giving me this kind of wiggle here. X to the fourth, a fourth power, will turn positive again. So a fourth degree will look a lot like a parabola with a couple of differences. It's going to be flatter as you're close to 0, and then much steeper as you get further away. And then the pattern will continue with x to the fifth being even flatter and even steeper, but I get back to that wiggle. And so we'll notice a couple of patterns. So two things that we'll want to observe here. As degree grows, the graph is steeper as we get further from 0, and flatter, closer to 0. The other observation is this alternating pattern of odd and even, giving us the bowl shape or the wiggle. So when degree is odd, the end behavior looks like this. And when the degree is even, the end behavior will look more like this. Of course, a transformation could affect this. If we had a reflection, then I may end up having the parabola point downwards, for example. But it's still going to end up being that for odd degree, the end behavior is the same in both directions, or excuse me, opposite for both directions, whereas for even degree, it will be the same. Let's go through an example here. I've got this very ugly looking polynomial. Fortunately, someone has factored it for us. Now, the first thing we're going to want to do when we're doing a sketch like this is determine the zeros. Looking at each of the factors, I can find a different zero. X equals 0 from the first one, 2 from the second, -1 from the third. The last one doesn't have a solution because x squared plus 4 will never be equal to 0. That would mean x squared would have to be equal to -4. So there's nothing that comes from here. We'll start by plotting each of these zeros. Since I'm making a graph that I would like to be roughly to scale, let's make sure I put on a scale. Next, I should make myself a number line. Where is my function positive and where is it negative? -1, 0, and 2. Now, I could plug in points here in order to get a sense of what's going on, but I can also do better if I notice the pattern. The pattern is that each of these pieces is where it could possibly change sign, the 0, the 2, and the -1. Now, at these pieces, it will change sign once for each factor. What do I mean by that? Well, notice that this x is to the third power. That means that right here, there are 3 pieces contributing to being 0, and all of them will change sign. 3 changes of sign means that I do end up changing sign. Compare that to the x minus 2 squared. Here I have 2 factors trying to change sign, and they'll cancel each other out. That means that instead of crossing the x-axis, I'm simply going to bounce off of it. At x equals -1, there's only 1 factor since it has no power, so the power is 1. Therefore, it will cross. So all we need to do is figure out where it's positive or negative at 1 point, and from there, we'll be able to figure out the rest. Well, let's say I plugged in a very large number. All of these different pieces would end up being positive. So I know when I come out the end here, it is going to be positive. At 2, I know that it's going to bounce off because the power on the x minus 2 factor is even. So I have something like this. At 0, I know it's going to cross. And at -1, I know it's going to cross. So I'll just have to fill in these gaps like this, and like this. For now, we're not going to put more detail into these graphs. We don't really care how high it goes. If we wanted more information, we could plot more points. It wouldn't be difficult to do so. But for the moment, this is the only detail that I want to see. Make sure we throw an arrow on the end. And we can double check the end behavior. The total degree of this function, 1, 2, 3, 4, 5, 6, 7, 8. Degree 8 should have end behavior the same on the left and on the right, and it does here. It's pointing upwards in both directions, so this seems consistent. There's one thing that you can do to help organize our thoughts here, which would be to track the sign independently on each of these factors. So x cubed, x minus 2 squared, x plus 1, and then x squared plus 4. For each of these factors, let's say I wanted to plug in the test values that I had from earlier. -2, -1/2, 1, and 3. Again, you could pick different test values if you would prefer. Let's look at what the signs will be for each of these. X cubed is going to be negative when the input is negative, and positive when the input is positive, because I'm simply cubing the number, so the sign won't change. X minus 2 squared is going to be 0 at 2, but positive for everything else because I'm squaring it. X plus 1 will be positive as long as the number that I'm using is greater than -1. Otherwise, it will be negative. And x squared plus 4, well, that will always be positive because I'm adding something squared to a positive number. Therefore, in each of these regions, I can simply count the number of positives and negatives to figure out what the answer is. So we can put maybe a total column here. Since the first one has 2 negatives, they cancel, and the final answer is positive. The bottom ones have only positives, so that's easy. The middle one has only a single negative, so the answer will be negative there. And what I end up seeing is exactly the same as what I got in my graph. It starts out positive, goes negative, goes positive again, and then bounces off 0, but turns positive. And I see that my number line gets a very similar pattern to the graph. Whether you use the table or whether you use the graph is entirely up to you. The idea of multiplicity is another term that we'll need. Multiplicity is the number of times a factor shows up. The fancy definition says that x minus a to the m will be a factor, but x minus a to the m plus 1 will not be. Let's take an example of multiplicity looking at the function in the previous answer. In this case, x minus 2 is squared, so I would say x equals 2 has multiplicity of 2. X cubed has a power of 3, so x equals 0 has multiplicity of 3. You can have multiplicity for the solution as well as for the factor, but typically we care about it more for the solution. One more thing we want to look at today is called the intermediate value theorem. The intermediate value theorem is something that we can use in order to determine where a function might have a solution. And here's the idea. Suppose f is a continuous function on the interval from a to b. If f of a is less than L is less than f of b. So let's take a look. Right here is f of a. Right here is f of b. And then there's some number L in the middle. If f is continuous and has this property, then there is some number c where f of c is equal to L. Simply put, all this theorem says is that if I have a function that between two x values has two different y values, and then there's some other y value in the middle, well, there's going to be an x value in the middle that when plugged into the function will give me out that y value. we can use the intermediate value theorem to guarantee that a function does something specific between 2 points. Most frequently, what we're going to do is we're going to say that my function, for example, goes from positive to negative or negative to positive. When the function does this and changes from positive to negative, well, we know that 0 is between the positives and the negatives. So we know that somewhere in there, there's going to be a 0. That's all we have for today. We'll see you guys next time.